All right, let's dive into one of the most crucial, but honestly, often overlooked parts of machine learning: feature engineering. You can think of it as the art of prepping your data to unlock its real potential. And believe me, it can be the single biggest reason your project succeeds or fails. So think about this for a second. Let's say you have a genius, the smartest person in the world, but you hand them a library full of jumbled, torn-up pages. Could they write a masterpiece? I mean, maybe, but it's not likely, right? You're setting them up for failure. And it's the exact same thing with a powerful machine learning model. And that is where feature engineering comes in. It's the solution. It's that critical pre-processing stage where we take those messy, torn-up pages of raw data and we carefully piece them together into a clean, coherent story that our model can actually understand. So, how do we actually do this? Well, we're going to break it down into a few key techniques. And to make this all really stick, we'll use a simple auto-loan dataset as our example as we go. The first step is feature selection. And it sounds super simple, but it is absolutely critical. We have to choose the most relevant pieces of data and, maybe even more importantly, get rid of all the useless junk, the noise that can just confuse our model. The more irrelevant stuff you have, the harder it is for the model to find the real patterns. And this is where it gets really intuitive, right? For an auto loan model, things like the car's year, its price, how many miles it's been driven, yeah, those are obviously relevant. But now, look at the other side. The car's color? Does a blue car make someone more or less likely to repay a loan? Probably not. That's noise. We'd want to get rid of that. Now, of course, you should always check with someone who knows the business before you just start throwing data away, but you get the idea. Okay, so once we picked our best features, now we get to do the fun part. We get creative. The next step is called feature extraction, and this is where we actually create brand new, more powerful information from the data we already have. We're basically building deeper insights for our model. And here's why this is so powerful. Instead of just giving the model the car year, we can calculate car age. Think about it. That's way more useful, because an older car might be worth less or cost more to maintain. Or check out step 2. Price per mile. Now that's a fantastic metric. It gives the model an amazing sense of the car's real value compared to how much it's been used. That's a much richer piece of information than just price or just miles on their own. All right, so we've got relevant, insightful features. What's next? Well, now we're going to simplify our data set and make it even easier for the model to handle. We're about to talk about dimensionality reduction. And I know that sounds super complicated, but I love this quote because it just cuts right through the jargon. It's not about deleting data. It's just a smart way of combining related features to capture what they mean together. Check this out. This is a perfect example using a popular technique called principal component analysis. Look at that top row. Instead of 3 separate features, loan amount, car price, and down payment, we can combine them into a single new feature we might call financial value. And we can do the same thing with car age and miles driven. Together, they pretty much represent the car's depreciation value. Just like that, we've taken 5 features and boiled them down to 2, making our model's job a whole lot easier without losing the important info. Okay, our data is lean, it's mean, it's meaningful. But we're not quite there yet. There are a couple more common problems we need to fix to make sure all our data is, speaking the same language. So here's problem number 1. Our dataset might have text categories like truck, SUV, or sedan. And here's the thing about most machine learning models. They're all about math. They fundamentally speak in numbers, not words. So we've got to translate. And the solution is a technique called categorical encoding. The simplest way to do it is right here. We just assign a unique number to each category. Truck becomes 0, SUV becomes 1, and sedan becomes 2. Now, we do have to be a little careful here because the model might mistakenly think that 2 is somehow more than 0. There are other ways to encode for that, but for now, the main takeaway is we've successfully turned our text into numbers the model can actually work with. And really, that's the bottom line, isn't it? This simple transformation is absolutely essential. At the end of the day, these models are built on math, and they just plain work better when we feed them the numbers they're designed for. All right, on to the next big problem in this section, scale. Just imagine for a second, you've got one feature, like a person's age, maybe ranging from 40 to 65. And then another feature is their salary, which could be over $100,000. That huge difference in the raw numbers can totally throw a model off. It might accidentally think salary is thousands of times more important just because the number is bigger.
The way we solve this is by putting everything on the same scale. As you can see, there are a couple of popular ways to do this. There's normalization, which squishes everything to fit between 0 and 1, and there's standardization, which is a bit different. It shifts the data so the average value is 0. The methods are different, but the goal is exactly the same. Create a level playing field so no single feature gets to dominate the model just because its numbers happen to be bigger.
So, after all that work, the selecting, creating, simplifying, and standardizing, what's the big deal? Why do we even bother with all this? Well, this is the payoff. What you get is a high-performance data set that's perfectly tuned for your model. And that leads to faster training, a whole lot less confusion for the model, and this is the most important part, way more accurate predictions. By cleaning everything up, we've given our model the best possible shot at success.
You know, at the end of the day, it all boils down to one simple truth. You can have the best, most sophisticated algorithm in the world, but your model is and always will be only as good as the data you feed it. So the real question I want to leave you with is, are you really engineering your data for success?